Go. All right, so it looks like we're back in business. Maybe I should look at the schedule first. So we are here. I'm gonna hope for doing some of 7.3 today. So I'm gonna go rapidly through 7.2 because you had technically all of last week to do that. But I'm gonna do a 100-mile-an-hour version of it. Okay, so again, hopefully you weren't just using last week as a vacation or holiday, that you actually tried to look at it. But so I will make the assumption that you saw some of it, either the announcements or the mini video that I gave. And so if I get up to 7.3, I'm okay. So I'm back. I think I'm sort of back to schedule. Remember back here, I said it'd be nice to get a little bit ahead in case something happens. Well, something happened, so I gave back those days. So now I think I'm still on par. So it's wise. I think it's a good idea. If I can get ahead, I will. Not just to go super fast for the sake of going super fast, but in case something happens, then I wouldn't have fallen too far behind. Again, last Thursday, pretend there was a quiz number 3 and you all got 5 points on it. And Thursday, I'll give you a quiz. I thought, since I didn't give you last week's quiz, why don't I just give you last week's quiz this Thursday? Okay, so quiz on Thursday at the end of class. It'll be on 7.1 and maybe 7.2 material. Okay, integrating by parts and maybe some of the 7.2 stuff. Okay, so that's where we're at. And everything here should be according to plan. And once again, don't be surprised if my problems don't match yours, because mine was from the 7th edition, and now we have the 8th edition. You're still learning the material. Okay? Now, on the first day of class, I said the best way for me to show you how to do the problems is to just do some of the problems, but that's not typical. A lot of teachers don't do that. So if I end up doing some problems which are not from the book, no big deal. A lot of teachers pick problems that are not directly from the homework. So the whole idea is that you're still learning the material. Right? So if you're still learning the material, the whole idea is that you get the knowledge on how to integrate by parts, how to do substitution and so forth. Okay? So that's what it's all about. All right, so I'm aiming to do 7.3 today. I'm going to do 7.2 fairly rapidly. Okay, so I will make the assumption you made some attempt to look at the notes and you had a chance to listen to the video while watching the notes. So I'm not going to go as slow as if I've introduced 7.2. So it will be somewhat rapid. Okay, so here we go. And once again, don't be surprised if some of the problems don't exactly match. Okay, so 7.2 somewhat rapidly. Again, ignore the dates. All right, so we know the derivative of the sine is a cosine. Derivative of the cosine is negative the sine. If you've forgotten, you can put it on your cheat sheet. Although again, if I were teaching you guys on campus, I would make you memorize it again, but we're supposed to lax off on you guys a little bit because of COVID. So one of the ways I'm letting you do that is to have a cheat sheet. Okay, and then these identities, sine squared theta plus cosine squared theta is equal to 1. So if you subtract cosine squared on both sides, you have sine squared equals 1 minus cosine squared. And notice if you subtract sine squared, it looks like this, cosine squared equals 1 minus sine squared. Okay? And so what I tried to get across to you several ways, whether effectively or not, I don't know, but we're trying to integrate sine to the m of x, cosine to the n of x. Okay, the easy scenario is if either m or n is odd, or maybe both. Okay, if at least one of them is odd, that's the better case. That's what you want. So by contrast, that means the harder case is if both m and n are even. Okay, so let's say if they're both 2, I've got an example of that. Or this is a 2 and this is a 4, that's considered harder. Okay, but if one of these is odd or both, then you're good. Okay, and here's why. Okay, so problem 1, at least my problem 1. Okay, integrate sine squared x cosine cubed of x. Okay, so this has an odd exponent. So this is considered the easier case. So the trick is take the odd and split it up into an even times an extra cosine. So sine squared x, cosine squared x times cosine x. So notice this is still cosine cubed, right? Still cosine cubed. And now the strategy is everything circled. I want all of that stuff to only say sine of x. That's why I put stuff with sine of x. Because if I have only stuff with sine, then I'll just say u equals sine x, du equals cosine x dx. Right, so everything circled, I only want sine. This is already sine. This is cosine squared, but no worries because I know cosine squared is 1 minus sine squared because I can rewrite cosine squared theta as 1 minus sine squared theta. Right? So my object is to make this stuff only say sine, no other trig function. So here it is. Cosine squared is 1 minus sine squared. So I now have sine squared x times 1 minus sine squared x times cosine x dx. Now this is perfect. I've got a bunch of stuff with only sines times cos x dx. So now I just do my u substitution. Okay, so u equals sine x, du equals cosine x dx. So this changes to du. This becomes u squared 1 minus u squared. That's no big deal. That's just another polynomial. I can multiply that out and integrate easily. Okay, so I want something of the form, a bunch of stuff with only sine times cosine dx. All right, so I have u squared times 1 minus u squared, which is u squared minus u to the 4th du. Okay, so that integral is pretty straightforward. U cubed over 3 minus u to the 5th over 5 plus c. And then just change u back. What was u? It was sine of x. So I usually like to write it like this. Now, if you want to leave it as divided by 3 and divided by 5, that's fine. But I like to emphasize that these are coefficients. So that's why I wrote it as 1/3 sine cubed x minus 1/5 sine to the 5th x plus c. All right, so that's my final answer. Notice this is an indefinite integral. Indefinite integral means plus c. Definite integrals don't need the plus c. Okay, so let's do number 3. Okay, sine to the 7th, cosine to the 5th. So that's considered easier. I have at least one odd exponent. Okay, so the easier one is either m or n or both is odd. Okay, so you have a choice here. Okay, so you pick one of the odd ones. Okay, so I pick cosine to the 5th. Write it as cosine to the 4th times an extra cosine. Right? Or I could make this sine to the 6th times a sine. That also works. So here we are. So I have separated out a cosine theta d theta, which now means everything behind my pen here, I want to have only sine of theta. I want to write it only as sine. Okay, so that's already sine. I need to change this to sine. So I have cosine to the 4th. Well, cosine to the 4th is cosine squared squared. That's what I have here. Sine to the 7th, cosine squared squared, that's cosine to the 4th, times the cosine theta d theta. Quick check of inventory. This is cosine to the 5th, is it not? Cosine squared squared is cosine to the 4th, and that extra one makes it cosine to the 5th. So you agree it is equivalent to what I started off with. Okay. And now I want all of this stuff, everything besides cosine theta, everything behind my pen, only to say sine of theta. That's already good. I have cosine squared squared, and we already know cosine squared is 1 minus sine squared theta. So I change this to 1 minus sine squared theta squared, and now I'm good. All of this junk right here only says sine of theta, only one trig function, times cosine theta d theta. Now I'm ready. Let u be sine of theta, du is cosine theta d theta, and I'm good. Okay, so u equals sine of theta, that becomes u to the 7th. This becomes 1 minus u squared squared. That's okay, it's just a polynomial. And this is a definite integral. So recall for definite integrals, I change the limits also. As theta goes from 0 to pi over 2, what happens to u? So I plug in here, u equals sine theta. So theta is 0, put a 0, sine of 0, 0. Okay. And then the upper limit is pi over 2. Plug in pi over 2, sine of pi over 2, 90 degrees. At 90 degrees, the sine of 90 degrees is 1. So I'm integrating from 0 to 1, my favorite. Okay, so sine to the 7th becomes u to the 7th. 1 minus sine squared becomes 1 minus u squared squared. Cosine theta d theta is du. So the whole problem is now in u. Okay, I had theta, d theta, and limits in theta. I now have u, du, and limits in u. I don't have to switch back to theta anymore. And now this is just some algebra. 1 minus u squared squared is this. That's like a minus b quantity squared, right? 1 minus 2u squared plus u to the 4th. Distribute u to the 7th. U to the 7th times that, times that, times that. So u to the 7th minus 2u to the 9th plus u to the 11th du. Okay, so u to the 8th over 8 minus 2u to the 10th over 10 plus u to the 12th over 12 from 0 to 1. Plug in 0, you get 0. Plug in 1, 1/8 minus 1/5 plus 1/12. You should show me this, okay? And I marked some of you down on this on the exam. On the exam, it was just arithmetic, but you should not go straight from there to there. I don't accept that. I don't accept you did it in your head because I can't do that in my head, right? So you get a common denominator, 120, and show me 15 times 15, 24, 24, 10 times 10, right? Show me that arithmetic, okay? Just like we did in class. Okay? Unless it's something that's very, very easy that I could do in my head, then I'll accept it. I could not do this in my head, so I'm not expecting you to do that in your head. And then 15 minus 24 plus 10, final answer of 1 over 120. Okay, skip this one. That was in the old edition, and we're never covering that anyway. But I just will mention that does qualify as an easier problem because there's an odd exponent. Okay, so now the harder situation. So far, we've only done odd exponents. So what if both m and n are even? All you see are even exponents. Like number 7. Integral from 0 to pi over 2 of cosine squared of theta d theta. And you might say, can I change cosine squared to 1 minus sine squared? Well, yeah, but then you'd still be trying to integrate sine squared, which is not going to be any better. Okay, so in that instance, use these formulas. Now, there was a double angle formula from Trig. Okay, cosine 2 theta equals cosine squared theta minus sine squared theta. Okay, you can take my word for it. You can do some algebra, and you can change cosine squared theta into this, and sine squared theta into this. Ignore this to be memorized. Last time I taught the course, I made everybody memorize it. Again, under COVID, you can put it on your cheat sheet, so never mind about to be memorized. Okay, but you can do some fancy footwork here and make substitutions like here, but just accept that you can do it. So cosine squared, 1 plus cosine 2 theta over 2, sine squared theta, 1 minus cosine 2 theta over 2. Okay. Sometimes they're called double angle formulas, and sometimes they're half angle formulas. Well, you know, this angle is half of that. All right, so to integrate cosine squared, just change it to this. So that's going to become 1 plus cosine 2 theta over 2. Okay? And that's hopefully straightforward. This uses the chain rule in reverse. So I'll take out the half. That 2 is a half there, okay? Integral of 1 plus cosine 2 theta. Integral of 1 d theta is theta. Integral of cosine is sine, not negative sine. We're not asking for the derivative. We're asking for the antiderivative. Okay? And then chain rule. Okay? If I were to differentiate, I would multiply by 2. Since I'm integrating, I divide by 2 or multiply by half. So there it is, theta plus a half sine 2 theta. Okay? You can double check by taking the derivative. Right? Ignore that 2, that's already outside. Let's differentiate this. What's the derivative of theta? 1. What's the derivative of half sine 2 theta? It's half cosine 2 theta times 2. That 2 cancels that half, so you get that. Okay, so from 0 to pi over 2, plug in 0, you get 0. 0 there, sine of 0 is 0. Okay, then I plug in pi over 2, put a pi over 2 there. If you put a pi over 2 here, 2 times pi over 2 is pi, and the sine of pi is 0. So that's 0. So everything's 0 except for that. So I have half times pi over 2. Final answer is pi over 4. All right, and then 11, which is a little bit harder, you have 2 evens, right? So this is considered the harder one. Sine squared x, cosine squared x. So change sine squared to 1 minus cosine 2 theta over 2. Cosine squared, make it 1 plus cosine 2 theta over 2. Okay. 2 times 2 is 4 on the bottom, so I take outside the 1/4. You can take constants out. The top is 1 minus cosine 2x, 1 plus cosine 2x. That's like a minus b, a plus b, which is a squared minus b squared. So 1 squared is 1 minus cosine squared of 2x. Okay. Well, 1 minus cosine squared is sine squared. So I change it to sine squared of 2x. Sine squared of 2x. I now go back and use this formula. Sine squared. Now 2x is an angle. If x is an angle, 2x is an angle. So notice to go from this formula to this formula, you double this angle, right? Twice this thing goes right here. So what is twice 2x? 4x. So it becomes 1 minus cosine 4x over 2. Okay, so one more time, I'm applying this formula. To go from here to here, you double the angle. 1 minus cosine, double the angle over 2. So 1 minus, whoops, where am I? Here I am. 1 minus cosine, double the angle. The angle was 2x, 4x divided by 2. All right, so there we go. That becomes 1/8 on the outside. Take the 2 out, 1/8. Integral of 1 is x. Integral of negative cosine is negative sine. And then by the chain rule times 1/4. Again, that's the chain rule in reverse of derivatives. If you took the derivative right here, when you get to this step, right, you would multiply by 4. So in this case, you multiply by 1/4. So x minus 1/4 sine 4x. Again, you can double check by differentiation. Take the derivative of this, you get that. Ignore the 2. 2 is already on the side. Plug in 0, you get 0. 0 minus sine of 0 is 0, so that's 0. Plug in pi over 2 here. Pi over 2 minus, put pi over 2 here. 4 times pi over 2 is 2 pi, and the sine of 2 pi is 0, so that's 0. So again, these are all gone. So I just have 1/8 times pi over 2. Final answer is pi over 16. Okay. All right, so that's it for that part. Okay. And the next thing I want to show you is this. Still 7.2. Ignore that. That was from the 7th edition. Yeah, I was trying to show you on the video and the attachment some basic integrals. So integral of cosine is sine. Integral of sine is negative cosine. Okay, I have the derivation of tangent of x. So if you want to follow along, you may. The trick is to make tangent sine over cosine and do a U substitution. Okay, ultimately, it's ln absolute secant x plus c. Okay, you can put it on your cheat sheet. If we were in class, I'd make you memorize it, but you can put it. So integral of tangent is this. Okay, integral of cotangent, the way to do it is to make it cosine over sine and do a U substitution again. If you do it the right way, ln absolute value of sine x plus c. So here's a quick summary of integral of tangent and cotangent. Okay, and I was just noticing a side note. This is pretty easy to check. What's the derivative of ln absolute value of sine x? Derivative ln of something is 1 over that, right? So you go 1 over sine x times the derivative of sine x, which is cosine x. So you have cosine x over sine x, which is the definition of cotangent. Okay, integral of secant x, the derivation is kind of weird. The trick is to multiply top and bottom by secant x plus tangent x. You say, why do you do that? It works. That's all we can say. It works. Okay, so if you distribute the top, it now looks like that. Secant squared x plus secant x tangent x. And believe it or not, the derivative of the bottom turns out to be the top. Okay, you might recall, what's the derivative of secant x from Calc 1? It's secant x tangent x. And what's the derivative of tangent x? It comes out to be secant squared x. So if you do a U substitution, it's perfect. Okay. Anyway, what it comes out to be is ln absolute value of secant x plus tangent x plus c. Okay. So again, if you want to put that on your cheat sheet, you may. So what's the integral of secant x? Ln absolute secant x plus tangent x plus c. Okay. And something very similar works for integral of cosecant x. That was problem 39, at least in the 7th edition. You can check and see if it's still there. But you do something similar to integrate cosecant. Okay, so the trick is to put cosecant x plus cotangent x, top and bottom. You also have to deal with a negative symbol there, but the process is very similar. So I'm not going to go over that for integral of cosecant. Okay, I do want to go over this now. How do you do integrals involving secant and tangent? Secant to the m, tangent to the n. Okay, so there's no hard and fast rule, unlike the ones for sine and cosine. If you have only sines and cosines, you want at least one odd exponent. Okay, there's no rule like that for secant and tangent, but we are going to say this. Okay, so from Calc 1, what was the derivative of the tangent of x? Secant squared of x. What was the derivative of secant x? Secant x tangent x. And we also have these identities from trig. Okay, 1 plus tangent squared x equals secant squared x. And if I subtract 1 on both sides, tangent squared x equals secant squared x minus 1. So that means if I have an expression that has secant squared, I can change it to tangent squared. And likewise, if I have something involving tangent squared, I can change it to secant squared. Okay, we're going to use that. Okay, so here are the two things that we're trying to look out for. If you have integral of secant to the mx, tangent to the nx. So we don't have an easy rule like do this if it's odd or even or whatever. Okay, but here's one thing to try. Because of this, one thing you can do is to try to have stuff with tangent x. That says stuff with tangent x. That means the only trig function here is tangent. It can be tangent squared, tangent cubed, square root of tangent, 1 over tangent, whatever, as long as you only see tangent. And then next to it, secant squared x dx. That way you'll let u be tangent x and du is secant squared x dx. The other option is taking advantage of this. Have a bunch of stuff with secant x. It can be secant cubed, secant to the 4th, square root of secant, 1 over secant. Doesn't matter, only secant, and then times secant x, tangent x dx. Okay, then you'll do a u substitution of secant x, and that becomes du. Okay, so I've got some examples here for you right now. Okay, so 21, tangent x, secant squared x dx. Okay, so I notice I can make this look like secant x, tangent x, like that. So I write it as secant squared x, secant x, tangent x dx. So do you agree this is the same as this, right? Secant squared times secant is secant cubed. Okay, so I'll let u be secant x because the derivative of secant x is secant x, tangent x dx. Okay, so I'm using this one, stuff with secant x times a secant x, tangent x dx. So u equals secant x, du is secant x, tangent x dx. So now this, all of this stuff here, secant x, tangent x dx, becomes my du. And instead of secant squared x, that's just u squared. And that's easy. So that's u cubed over 3 plus c. And change u back to secant. So 1/3 secant cubed x plus c. Okay, 23 doesn't really fit that category. Okay, so how do you integrate tangent squared? The key is change tangent squared to secant squared x minus 1, and we know how to integrate that. Okay, so integral, where'd it go? Lost it. Yeah, integral of tangent squared x is secant squared x minus 1. And what's the integral of secant squared? Tangent. So it's tangent x, integral of -1 is negative x, so tangent x minus x plus c. And there we go. Okay, this one I crossed out by mistake, sorry about that. So I'm going to keep it, ignore that. Okay, tangent cubed x, secant x dx. So you can see I can extract out a secant tangent, right? So do the same trick. Make this as tangent squared x times secant x, tangent x dx. So there, these two combine to be tangent cubed, right? Tangent squared times tangent. Okay, so I have secant x, tangent x. That means I want this stuff to only say secant. So behind my pen, I only want it to say secant. Right now it's tangent squared. How do I change it to secant? Well, we just did it back up here. Secant squared x minus 1. Right? So I'm taking advantage of this right here. So tangent squared x is secant squared x minus 1. So now I have a bunch of stuff with secant times secant x, tangent x dx. So now I can do my u substitution. U equals secant x, du equals secant x, tangent x dx. So all of this stuff here becomes du. And instead of secant squared x minus 1, u squared minus 1 du. And now that's easy. So u cubed over 3 minus u plus c. Change u back. So final answer, 1/3 secant cubed x minus secant x plus c. Again, I like to rewrite this as instead of dividing by 3, it's a little bit awkward. I like to write it as multiplying by 1/3. Emphasize it's a coefficient. Okay, then 29. Should be a dx there. Tangent cubed secant to the 6th. Okay, that's a pretty high exponent. Okay, but I can write it so that there's a secant squared there. Okay, so secant to the 6th is secant to the 4th times secant squared. Right? All right, so there's secant squared. That means I want the rest of the stuff to only involve tangent x. Okay, so everything behind my pen right now should have only tangent. That way I'll let u equal tangent and du is secant squared x dx. Okay, so this stuff and this stuff, I only want tangent. This one's already tangent. I need to change this to tangent. Well, secant to the fourth is secant squared squared. And now I know how to change secant squared to 1 plus tangent squared. Right here, 1 plus tangent squared x equals secant squared x. So that got changed to that. And now I have a bunch of stuff that only says tangent. Tangent cubed, 1 plus tangent squared, squared, it's all tangent. So now let u equal tan x, du is secant squared x dx. Okay, so now I'm going to have a polynomial after I do all this. Okay, so u equals tangent x, so that becomes u cubed, 1 plus u squared squared times secant squared x dx is my du. And there we are. Right, so I do that algebra. So u cubed times 1 plus u squared squared is this, 1 plus 2u squared plus u to the fourth. And then you distribute. So u cubed times all that. U cubed plus 2u to the fifth plus u to the seventh du. Okay, then we're home free. So u to the fourth over 4, 2u to the sixth over 6, u to the eighth over 8 plus c. Change u back to what it was, tangent. So 1/4 tangent to the 4th x plus 2 over 6 is 1/3 tangent to the 6x plus 1/8 tangent to the 8x plus c. And there we go with that one. Okay. Okay, now 31 I did not show you. I may have given you the handout for the attachment for that. But I don't think I actually went over it. It's a much longer problem. Integrate tangent to the fifth. Okay, so I'm going to show you how to do tangent to the fifth. It's pretty long. In fact, it's so long, it goes all of this and up to here. So here's an instance where you have a lot of I1s, I2, I3, I4. Okay, so I will always represent the original for me. All right, so how do I possibly do tangent to the fifth? Okay, so I first write it as tangent cubed times tangent squared. Okay, and I change tangent squared to secant squared minus 1. Okay, so I'm using these identities, where'd they go? Right here, tangent squared is secant squared minus 1. Then I distribute. So distribute tangent cubed secant squared minus tangent cubed. Okay. These are integrals all in themselves, so I'm going to split this up. Okay, so I'm going to write it as integral of tangent cubed x secant squared x dx minus integral of tangent cubed x, and I'll work these out separately. So I'm going to call this I1 and I2. So the original integral is always I. Within the same problem, sometimes you're doing a first integral, a second integral, maybe even 4 integrals within the same one basic integration problem. So I relabel them as I1 and I2 and so on. So it's like I take a timeout, figure out I1, take another timeout, figure out I2, and then once I have that, I put them all together. Okay, so my timeout to figure out I1, tangent cubed secant squared. Okay, that's nice. That's of the form stuff with tangent times secant squared. In other words, that fits this category. Stuff with tangent times secant squared. Okay, so where am I? Okay, so u equals tan x, du equals secant squared x dx. This changes to du. This is u cubed. So that's easy. So u to the fourth over 4 plus c1. You've probably not seen this before, but you can't just write c, okay, because if you put plus c here, and I'm going to do another integration problem, put plus c there, you're implying these c's have to be the same, but they do not have to be the same. So I'm going to write C1, C2, and so on. Yes, the final answer, you put them all together just as C. But very technically, for this sub-problem, you have to write it as C1. Okay, so this is my I1. Okay. So I1 is done. Now I have to figure out I2. Tangent cubed. So timeout, figure out tangent Q. So I write it like this. Tangent squared times tangent. Change tangent squared, again, secant squared x minus 1. We just did that. Distribute. At tan x times secant squared x minus tan x. This one I'm going to break up into two. Okay. Sometimes you hear the integral of a difference is the difference of the integrals. To integrate the whole thing, you're going to integrate that, integrate that. So I break this up into tan x secant squared x. I'm going to call that I3 minus integral of tan x dx. That's I4. So even though I have the original integral I have four separate integrals in the same problem that I have to figure out. So I now have I1, I2, I3, I4. So I was working on I2. Okay, so that's why I label it. There's so many integrals going around sometimes to avoid getting lost. You can label it like such. Okay? And for you computer science people, you can see the analogy for computer science, right? You have a program, then you call a subprogram or a subroutine, right? It's like you take a timeout, figure this out, okay, bring it back to this subprogram, and then finally bring it back to the main program. Okay. If you're not in computer science and you have no idea what I talked about, that's okay, don't worry about it. But I like to give things that are relevant to some of you sometimes. All right, so I3 minus I4. So I3 is tangent times secant squared. That does fall under this category, stuff with tangent and secant squared. So here we go. U equals tan x, du equals secant squared x dx. That becomes u, and that's du. So integral of u du, u squared over 2 plus c2. Okay, again, it's more accurate to put c2. You should not put plus c, because if you put plus c here and plus c here, that implies those c's are the same, but they do not have to be the same. So that's why you label them c1 and c2. So now I have 1/2 tangent squared x plus c2. All right, and then I4 is the integral of tangent. Well, I just showed you that. That's ln absolute value of secant x plus c3. Right? So remember, look back in your notes. Integral of tangent was ln absolute secant plus c3. And finally, I start putting everything back together. Okay, and see if I can show you that right here again. Yeah, integral of the tangent, ln absolute value of secant. All right, so we said I2 is I3 minus I4. So I3 minus I4. So it's 1/2 tangent squared x minus ln absolute value of secant x plus, I'll just call it C4 right now. Okay. Yes, there's a C2 plus a C3. I'm going to call that C4 now. Okay, you're just putting two constants together. So this is I2. Finally, I go back to I equals I1 minus I2. Okay. So you just go back to the original. So I1 was that, and minus I2 is all this mess. So now I'm good. 1/4 tangent to the 4th x minus parentheses 1/2 tangent squared x minus ln absolute value of secant x. And now that you have this, you say, well, I got all these constants. I got C1, C2, C3, C4. Yeah, when you take C1 plus C2 minus C3 plus C4, whatever, now you can finally just put plus C. And there we are. Okay. All right, so that was my 100 miles per hour version of 7.2. So that was theoretically all of last week's stuff. And now I can get started with 7.3. Okay, and what time is it? 10 minutes to 8. Okay, so I'll do a little bit of 7.3, and then we break, and then we'll do some more. So 7.3 is on trig substitution. Now, there's a table here at the bottom of 486. Okay, you can have this on your cheat sheet. You don't have to memorize it. To make it a little bit easier for you, I think the only things you really need are right here. Okay, so put this in your cheat sheet. They have 3 versions of funny square roots. It's a square root of a squared minus x squared. Then they say x equals a sine theta. This is square root of a squared plus x squared. X equals a tangent theta. Square root of x squared minus a squared. X equals a secant theta. Okay. Don't worry about these. This just means the angle is in the quote-unquote right place. Okay. These are identities that you'll need. Okay. Theoretically, you already know this one, and we've talked about this already. 1 minus sine squared equals cosine squared. 1 plus tangent squared equals secant squared. And secant squared minus 1 equals tangent squared. Okay, so put these on your cheat sheet. And I'll tell you what, I know what I'll do. Since you might not be able to see that, I'll go ahead and write it. Okay, so I'm going to try to write these on paper. Of course, my writing's not that good either necessarily. Okay, x equals a sine theta. So put these on your cheat sheet. Square root of a squared plus x squared. X equals a tangent theta. And square root of x squared minus a squared. You substitute x equals a secant theta. Okay, so here's the same thing. You can write it down now or not. It's on the video. You'll get the video later, but that's the same thing. Okay, what's going to happen now is we're going to get some integrals that have these funny square roots. By making these substitutions, you turn it into a trig integral, which is much, much nicer. Okay, so you have to figure out the a. Well, they give it to us normally as a squared. So let's say this was 25, then a would be 5, right? Or let's say this was 16, then a would be 4. Or a squared is 9, then a would be 3, and so on. By making use of these substitutions, okay, so I'm going to make this disappear now. Okay, and you can always look at the video. By making use of these substitutions, you end up with a fairly nice integral. All right, so we have this. Okay, and then before I get started with the problems, we have to review some right triangle trigonometry. Okay, so let me put this down here. You can write it or not. You all already know this. And you can look at the video later. But remember from trig, right? If you have a right triangle, 90-degree angle, and here's theta, this is called the opposite side, right? OPP. This is the adjacent side, ADJ, and the hypotenuse. Quick reminder, the hypotenuse is always opposite the 90-degree angle. Okay, so at first glance, you might say, why is this the adjacent? This could also be the adjacent. After all, it is next to theta. Yeah, but this already has a name. It's already called the hypotenuse. So the side which is not the hypotenuse that's next to the angle is adjacent, right? And then you might remember this mnemonic device in trig, Socatoa. Have you ever heard of Socatoa? Okay, so, S-O-H, that means the sine of theta is the opposite divided by the hypotenuse, right? And ca, C-A-H, cosine of theta is adjacent over the hypotenuse. And toa, T-O-A, tangent of theta is opposite over the adjacent. Okay? So we have to use this for the homework problems in this section also for 7.3. Okay, so Socatoa, right? Sine opposite over hypotenuse, cosine adjacent over hypotenuse, tangent is opposite over adjacent. Okay, so we'll be using this. All right, so let me just show you a little bit of what the problems look like. I might do 1 or 2 of the most and then we'll break. So now we're trying to integrate crazy looking stuff like this. And we're now on page 491. And notice a lot of these problems have these funny square roots in there, right? So how do I tackle that? I tackle that by making use of these substitutions, right? So you have to figure out what case you have, which situation you have, and then make these various substitutions. Okay. Now, 1, 2, and 3 are one of each. That's why I wanted to do all of them. 1, 2, and 3. So I wanted to show you at least 1, 2, and 3 today. Okay. Unfortunately, they already gave us a hint. Okay. So as we do the problems, I don't want you to look at this. Okay. So pretend these hints aren't there. If you've already seen it, it's too bad, too late. But I want you to be able to look at that chart, look at this thing, right, and determine which of these scenarios apply. Okay. So I'll get started with some of these, and it's almost 8 o'clock, so we'll see. Okay, so number 1, I was going to show you 1, 2, and 3 because it shows you each of these 3 cases that we have here. Okay, so let me lose this. And so again, what we're looking for is which of these applies. There's only one plus, so if you see a plus, it's automatically x equals a tangent of theta. But there's 2 cases for the minus. In case you're wondering why aren't there 2 cases for the plus, well, it's very simple. I mean, here you just turn this around, right? A squared minus x squared, x squared minus a squared. So how about if I turn this around? Well, addition is commutative, right? A squared plus x squared. If you turn it around, x squared plus a squared is the same thing. So you don't need a new formula for that. But this is not the same as this in algebra, right? You know that a minus b is not the same as b minus a. Like 5 minus 7 is not the same as 7 minus 5. But 5 plus 7 is the same as 7 plus 5. So that's why you don't need another formula for x squared plus a squared. It's the same formula, right? Okay. So here we go. Number 1, integral of dx. If it says dx, you pretend there's a 1 dx, over x squared, radical 4 minus x squared. Okay? 4 minus x squared, that's a squared minus x squared. Right? So one more time. Don't even look at this x squared here. You're looking at the square root. And it doesn't matter if the square root's on the bottom or the top. It's square root of 4 minus x squared. That's like a squared minus x squared. All right? So that's like this. So my substitution is a sine theta. If the number here was 4, then what's the a? A is 2. So my substitution is x equals 2 sine theta from my chart. Okay? So x equals 2 sine theta. Dx is 2 cosine theta d theta. The derivative of 2 sine theta is 2 cosine theta d theta. Okay, and now I do a bunch of substitutions. So here's all the substitutions. Dx. What is dx? All this stuff. How do I know? It says so right here. Dx, 2 cosine theta d theta. There's my dx, right? Now I substitute x squared. All right? X squared is 4 sine squared theta. Agreed? And then radical 4 minus x squared. Well, we just did the x squared. So it's 4 minus 4 sine squared theta. Okay? Now here's the nice thing about making the substitution. I mean, you look at this, how messy the square root 4 minus x squared. But this is going to get rid of the square root, believe it or not. Okay, 4 minus 4 sine squared theta. I can factor out the 4. So it's 4 parentheses 1 minus sine squared of theta, right? What's 1 minus sine squared? It's cosine squared. Okay, so I leave this alone, leave this alone. Underneath the radical, I now have 4 times cosine squared theta, whose square root is 2 cosine theta. Okay, so that's the whole idea. Okay, notice how nice it came out by making use of this substitution. By making this substitution, I no longer have the square root by means of the identity. Okay, so 4 parentheses 1 minus sine squared, that's 4 cosine squared, whose square root is 2 cosine theta. And notice very conveniently, 2 cosine theta cancels 2 cosine theta. So I have a 4 on the bottom, which I'm deciding to take out, 1/4. Sine squared on the bottom. Now, sine squared on the bottom means cosecant squared on the top. Right? The reciprocal of the sine is the cosecant. Okay, remember, there's a trick. If one trig function has a co, the reciprocal does not have a co. So sine, right? Sine doesn't have a co, so reciprocal is cosecant squared. Okay? Integral of the cosecant is negative cotangent. So I have negative 1/4 cotangent theta plus c. Okay? And you might say I'm done. Okay? It looks like I'm done, but look at the variable you got. Theta. What was the original variable? X. So you can't leave it like that. Okay? So right now, calculus is done, and now we've got to start trig. I have to rewrite this expression in terms of x. So how do I do that? Okay, by the way, what's cotangent? Well, tangent was opposite over adjacent. So cotangent, you flip it, adjacent over opposite. Cotangent is adjacent over opposite, right? Okay, so now I draw my triangle. I have x equals 2 sine theta So divide both sides by 2. Sine of theta equals x over 2. All right, sine is what over what? Opposite over hypotenuse. So I draw myself a triangle, theta, opposite over hypotenuse, x over 2. Okay, so x, 2. I do some a squared plus b squared equals c squared to find this side. You can do it. It comes out to be radical 4 minus x squared. That's easy. What you can do is temporarily call this y. Then you have x squared plus y squared equals 4. Do a little bit of algebra. Y comes out to be radical 4 minus x squared. All right. Finally, I can go back and plug in. So I want negative 1/4 cotangent theta plus c. Negative 1/4. So cotangent is adjacent over opposite. All right. So adjacent is radical 4 minus x squared. And then the opposite was x. So there we go. And just combine it. 1 times the square root is just a square root. 4 times x is x. So final answer, negative square root of 4 minus x squared divided by 4x plus a constant c. So finally, that's my answer. Okay, so it was a pretty long process, as you can see. There's a lot going on in this problem. Okay, so I'll summarize quickly what went on, and then maybe we'll break after that shortly. Okay, look in the table for the correct substitution. Okay, so this one looked like 4 minus x squared. That's a squared minus x squared. That's the first one, where a is 2. So let x be 2 sine theta. Find your dx. Change dx to that. Change x squared to 4 sine squared x. If you do it the right way, the square root always comes out nice. Do the integral. Your answer is going to involve theta, but you can't leave it like that. You got to change it back to x. So then you use your Socatoa stuff, draw yourself a triangle, and figure out all the other sides. Okay. All right, so I think it's a good time to break now. So it's a little bit after 8. Okay, how about let's start up again at 8:15? Okay, so we'll break until 8:15ish. So let me stop the share and stop the recording.